Okay, so let's get started with this example. So we have steam steadily flowing through an adiabatic turbine at a rate of 1 kilogram per second. It enters the turbine at 5 megapascals and 600 degrees Celsius and exits at 50 kPa and as a saturated vapor. We want to determine the actual power output of the engine and the isentropic efficiency of the turbine. Okay, so I am going to draw a picture first. So we have a turbine, which we usually cartoonize in this way. So we're going to always have power coming out of this, and I'm going to call it the actual power. And then we have flow coming in and out. So this is our inlet, this is our exit. And we're given several things. So we know that this is water. So we have a stream of water coming in and out. At the inlet, we know that the pressure is 5 megapascals and the temperature is 600 degrees C. And then at the exit, we know that the pressure is 50 kPa and that it is a saturated vapor. Okay. Okay, so let's talk about what we want to find. So we want to find the actual power output. So that's this guy. So we want to find W dot A. And we also want to find the isentropic efficiency, which is eta T. Okay. Oh, and I forgot to write, we're given a mass flow rate too. So m dot is 1 kilogram per second. All right. The problem also tells us some useful things for solving it. So the first one is that we have steadily flowing steam. We're also told that it's adiabatic. Okay, and I think we've written down everything else here. Okay. Okay, so the first thing that we're going to do is we are going to write down our drawer control volume. So is this an open or a closed system? First off, it's open, right? So this is an open system because we have mass flowing in and out. And so our control volume is just going to be the turbine itself. All right, so that's our control volume. The second thing we're going to do is we are going to write down our governing equations. So we have conservation of mass. So we have the time rate of change of mass in our control volume is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out. And we also have conservation of energy. Which is the time rate of change of the energy inside of this control volume is equal to Q dot for the control volume minus W dot for the control volume plus the sum of the energy flowing in with the mass flow rate. So we have m dot in times the quantity of enthalpy coming in plus the kinetic energy coming in and the potential energy coming in. And then minus the energy flowing out. So all those same terms, but just for the exit. So we have enthalpy coming out, kinetic energy going out, and then potential energy going out. Right? All right. We also have an equation for isentropic efficiency. So we know that eta for a turbine is W dot A over W dot S. So this top one, this is our actual power. And then eta S is our ideal power or isentropic power. Okay. And those are all of our equations that we need. Okay. So just to remind you, we are looking for W dot A, and then we're also looking for eta T. Okay, so next, let's write down our simplifications and assumptions. Okay, so first one is, it's already written in the problem, so we're assuming this is steady flow, right? So steady means that the time derivatives go to 0. So I can get rid of the dmdt term and the dedt term. The problem also tells us that this is adiabatic. What does that mean? Anybody remember? No heat loss or added heat. So this means that our Q dot CV term is 0. So I can get rid of this guy. Anything else that we would like to assume? Yeah, we're going to neglect kinetic and potential energy. So when we get rid of our kinetic energies, we're going to get rid of these V squared terms in the energy equation. And then when we neglect potential energy, we're going to get rid of the GZ terms in the conservation of energy. All right. One other thing that I'm going to note here is that we have a 1 inlet, 1 outlet system. So I can get rid of these summation signs because they're summations over 1, right? So far, so good? Okay, so the next thing that I'm going to do is I'm going to write out my simplified equations. So for mass, I just have that 0 is equal to m dot in minus m dot out, which means that the mass flow rate in is equal to the mass flow rate out, which let's just call that m dot. There's only one mass flow rate to concern ourselves with, okay? For energy, this equation becomes 0 is equal to minus W dot of the control volume plus M dot HI minus HE. Right? And remember that W dot for the control volume is equal to W dot in minus W dot out. No, sorry. W dot out minus W dot in. And we're calling W dot out as W dot A, right? So this is our actual power output. Okay. So that means that this equation is W dot A is equal to M dot HI minus HE. Feel okay so far? Okay. All right. And then one other thing that I want to make mention of here. Actually, I'll wait. We'll do that in a second. Okay. So let's figure out W dot A first, because in order to find the efficiency, we need W dot A. So let's do that first. So we're going to solve for W dot A first. All right, so we have that W dot A is M dot times HI minus HE. We know M dot, that's given to us in the problem. We just need to find the enthalpies, right? So let's do that. So first, let's do our inlet state. So we have a pressure and a temperature. So PI is 5 MPa and TI is 600 degrees C. Okay, so for 6 megapascals, or sorry, 5 megapascals, we're looking here. And we know that TSAT is 263.94, but we have a temperature of 600 degrees C. So what does that mean about our state? It's a superheated vapor. Okay, great. So I'm going to put this back in the notes. And I think this is actually A5. So TSAT at PI is 263.94 degrees C. So this is a superheated vapor. Okay. Okay, so let's go to our superheated vapor table. And we're going to go to the 5 MPa pressure cell, which is here. And then we'll look at 500 degrees C, or no, sorry, 600 degrees C. All right, so I'm going to copy this. So that means that we have H at the inlet is 3666.9 kilojoules per kilogram. Okay. So see next page. Any questions so far? Okay, so now we just need the exit enthalpy. So we have that at the exit, we know our pressure and we know we have a saturated vapor. So we have that the exit pressure is 50 kPa. And we are a saturated vapor. All right, so which table should we use to find HE? Yeah,
Temperature if it's adiabatic.
say this again.
I don't know the temperature if it's an adiabatic process of the exit.
Good question. Hang on, I'm thinking. Well, let's check. So we can go to our pressure table, which is here. All right, so we know the exit pressure is 50 kPa. And if we're a saturated vapor, we have to have the saturation temperature, right? So this, oh, that is not a highlighter. Okay, so this is our saturation temperature, which is much different than our inlet temperature, right? So the temperature does change even though it's adiabatic. Okay. All right. Okay, so I'm gonna take a little screen grab of this. And we want the enthalpy, and since we know it's a saturated vapor, we're going to use Hg. So we are going to be looking at this column here. Okay, so we have that the exit enthalpy HE is 2,645.2 kilojoules per kilogram. Okay. All right, and so that means that we can now find W dot A. So our actual power is going to be M dot, which I think is 1 kilogram per second. Yes, so we have 1 kilogram per second times the inlet enthalpy, which is 3666.9 kilojoules per kilogram minus 2645.2 kilojoules per kilogram, which gives us 21.7 kilowatts. All right, so this is one of the items we were looking for, so we're done with that. Right? Any questions on that one? No? Okay, so now we want to find our isentropic efficiency. Yeah, our isotropic efficiency. So this is our A to T. So we know that A to T is equal to W dot A over W dot S. We already found W dot A, but we need to find W dot S, right? Okay, so let's consider how we would find our ideal output. So I'm going to draw a picture that we saw last time in the notes. So we have our ideal turbine where we have an output ideal power, W dot S, and we have our inlet is the same. So we still have our 5 megapascal, 600 degrees C inlet conditions. And we have HI is 3666.9, just like before. So in these problems, our inlet conditions are always going to be the same for actual versus ideal. But the exit is where it changes. All right. So our exit, we still have the same pressure. So we maintain the 50 kPa pressure, but our entropy at the exit has to be the entropy at the inlet, because this is an isentropic process. So isentropic means entropy stays the same. All right, so that means that our entropy, whatever our entropy is at the inlet, it's going to be the same at the outlet. And so we're going to use pressure and entropy to figure out the enthalpy at the exit. Okay, does this make sense? Okay, so first things first, if we want to find entropy at the exit, we need to find entropy at the inlet and to say that they're the same. Okay, so let's find SI. And I think, yes, so we're going to go back to this green starred table. And so our entropy at the inlet is here. So we have 7.2605. Kilojoules per kilogram Kelvin, which means that that is also our exit entropy. Okay. So that means we need to go back to our pressure table. And for 50 kPa, we need to figure out where this entropy lies on the PS diagram. Okay, so now use PE and SES to find state and HES. Okay. So if we look at a pressure entropy curve, we want to figure out what state we're in, and then we can use that information to find HES. Okay. Okay, so let's go back to our pressure table. Did I already put this in the notes, actually, I think? Oh yeah, okay. So we're still at 50 kPa, so we're still at that bottom row here. But now we want to have a look at SF and SG. So SG is 7.5931, which is greater than SES. So what does that tell us? What state are we in? Yeah, mixture, right? So since SF at P equals 50 kPa is equal to 1.0912 kilojoules per kilogram Kelvin, and SG at a pressure of 50 kPa is equal to 7.5931 kilojoules kilogram K. This means that our isentropic exit state is between these two things. So this is a mixture. All right, so that means we're going to have to interpolate to find H, right? So we interpolate to find HES. Okay, so I'm going to make a little table. I have HES and I have S. Oh, I'm sorry. H and S. So we have HF is equal to 340.54. And then SF, we already wrote down, is 1.0912. Then we have HES, that's what we're trying to find. And we have SES is equal to 7.5931. No, sorry, that's SG. So this is 7.2605. And then this is SG. And HG is 2645.2. All right, so then we just interpolate this to find HES. All right. And when we solve this, we get the following. So we get a value of 2,531 kilojoules per kilogram. All right, and so that means that we can now calculate our isentropic power output for our ideal system. So this is just m dot HI minus HES. All right, the equation, the energy equation stays the same for our ideal system. We're just changing what the output enthalpy is, okay? So we have our 1 kilogram per second, and then our inlet enthalpy is 36669 minus our ideal exit enthalpy is 2531. This is kilojoules per kilogram. All right, so we get that our isentropic power output is 1136 kilowatts. All right, so I can plug this back into my equation for eta. So I have eta T is equal to W dot A over W dot S, which is 1021.7 kilowatts divided by 1136 kilowatts, which gives us 0.899. So this is an 89.9% efficient turbine. Any questions on the process? Yeah.
Define SES.
SES is just the same thing, same as the input entropy. The input entropy, so when we figured out state one, so if we go back to state one, we said, okay, we looked at pressure and temperature. It's a superheated vapor. So I went to our superheated vapor table and went to the pressure cell for 5 megapascals. So that's over here with the green star. And so originally we were just looking at enthalpy. So I just grabbed that H value, but we could also grab the entropy at the same time.
Okay.
Does that make sense?
Yeah.
Cool. Other questions? No? A little tedious, but not too bad. Okay, great. Okay. So we've looked at turbines. Let's now look at compressors and pumps. So for turbines and pump, or sorry, for compressors and pumps, under steady conditions, the inlet state of the fluid as well as the exit pressure are fixed. Between actual and ideal systems. All right, so this is similar to what we just looked at for the turbine. So if we have an actual system and then we have an ideal system. So this is our pump. And at the inlet, we're going to have pressure, temperature, enthalpy, entropy, and a flow rate. All right, and then we're going to be inputting power into a pump. So we have W dot A. Right, so compressors and pumps always require power to be input to them. And then at the exit, we are going to have an exit pressure, an exit temperature, an exit enthalpy, and an exit entropy. Okay. For our ideal system, a lot of this is going to remain the same. So the inlet conditions are all going to be the same. So we have our same inlet pressure, temperature, enthalpy, and entropy, and flow rate. But we're gonna have a few differences. So this will have a different power input. So this is our ideal power input. All right, and for the exit, we are going to keep our exit pressure the same, but everything else is going to change. So we have our exit temperature, that's isentropic, our exit enthalpy, that's isentropic, and then our exit entropy, which is also isentropic, which means this has to be the same as our inlet isot. Our inlet S, okay? Entropy. Okay, does that make sense? So we're keeping all the inlet stuff the same, exit pressure is the same, and then outside of that, our exit temperature, enthalpy, entropy, and input work are all going to be different. Okay? Okay, so if we look at our conservation of energy equation, where we neglect changes in kinetic energy, changes in potential energy, assume adiabatic, and steady, then our conservation of energy looks like the following. So we have for our actual system, we have W dot for the control volume is equal to M dot HI minus HE. And for our ideal system, we have W dot of our control volume is equal to M dot HI minus HES. Okay. Now remember, W dot for our control volume is outlet work minus inlet work. So we have minus W dot A is equal to M dot HI minus HE. And then this is W dot S, which is negative, is equal to M dot HI minus HES. Okay. Okay, so if we wanted to know how the work input to an actual device is going to compare to that of an ideal device, we can look at the entropy balance. So how do W dot A and W dot S compare? Thinking about this intuitively, how should they be related? Which one should be bigger, do you think? S should be bigger. Mark thinks S should be bigger. Anybody else? Any other ideas? Why do you think so, Mark? Okay, so let's think about this because this is an opposite system as a turbine, right? So for a turbine, we're getting work out. So an ideal system should get more work out, right? But for a pump, should it take more work to power that pump and get the same result for an ideal system or an actual system? Yes, so W dot A should be greater than W dot S, right? So intuitively, we expect that it's going to take us more power to run our actual system over an ideal system. All right, but let's show this with the math, right? So if we look at our entropy balance, we have the following. So we have our change in total entropy of our control volume over time is equal to the sum over each of the little boundaries at different temperatures of Q dot J over the temperature at the J location plus M dot SI minus SE plus generation of entropy, right? So since we were saying this is a steady system and it's also adiabatic, then we get rid of these two terms, which means that we have m dot times SE minus SI is equal to S dot gen. So I haven't picked up a minus sign because I flipped the order of SE and SI. Okay. And we know that S dot gen is always greater than or equal to 0. Right? So this means that the fluid entropy always increases for our actual system, right? So as it flows through the pump, and then if we look at the Mollier diagram, which is just an HS diagram, it looks like this. So we have H enthalpy versus entropy. All right, and then this is our isobar. So this is our PE isobar. All right, so we know that our exit pressure has to stay the same. So if we start at our inlet state on this isobar, so this is PI isobar. An actual process curves like this. So this would be our actual exit pressure, or I'm sorry, our actual exit enthalpy. And then our ideal enthalpy has to follow an isentropic process. So S stays constant. So we're just on a vertical line here. So this is ES. All right, so we can see that HES is less than HE. And so since HE is greater than HES, W dot A is always going to be greater than W dot S. All right, so we can prove what we kind of already know just from thinking about this using conservation of energy and the entropy balance. Okay. Efficiency values for a compressor or a pump are going to look similar to what we did for a turbine, but we're going to flip it. All right, so it is going to be defined as the ideal input over the actual input. So this is ideal input over actual input. All right, because we always want this to be less than 1. So this is always less than or equal to 1. Okay. Make sense? So kind of a variation on a theme from what we did with the turbine. And we are going to do, okay, so we are essentially going to do a very similar example, but with a compressor this time. So we have air that's compressed steadily by an adiabatic compressor from 100 kPa and 12 degrees C to a pressure of 800 kPa and at a steady rate of 0.2 kilograms per second. If the isentropic efficiency of the compressor is 80%, determine the required power input to the compressor and the exit temperature of the air. We may assume a constant specific heat. Okay? So I'm going to draw a picture here. So here is our compressor. So we are inputting work. This is my actual work. We have an inlet and an exit. So our inlet conditions are a pressure of 100 kPa and a inlet temperature of 12 degrees C, which is 285 Kelvin. So since we're working with air, I'm going to be very careful to make sure I'm using absolute temperatures. Okay. And then we're exiting at a pressure of 800 kPa. And we don't know what the temperature is at the exit, but we would like to find it. And then we know that this compressor has an efficiency of 80%, which is 0.8. And we would like to find a couple of things. So we would like to find W dot A, and we'd like to find the exit temperature. Does this make sense? Okay. So I am going to first mark up some keywords in the problem statement. So first one is that we are using air. So this is important to note. We are also assuming that this is moving steadily and that it's an adiabatic compressor. Okay. All right, so the first thing that I'm going to do is I'm going to draw my control volume because this is, again, an open system. Because we have mass flowing in and out. So it's just going to be the volume of the compressor, like so. The second thing I'm going to do is write out our governing equations. All right, so we have conservation of mass and conservation of energy, just like before. So our conservation of mass is the time rate of change of the mass in the control volume is equal to the sum of all of the inlet mass flow rates minus the sum of all the exit mass flow rates. And then our conservation of energy is the time rate of change of the total energy in our control volume is equal to Q dot for the control volume minus W dot of the control volume plus the sum of the energy coming in through the mass transfer. So we have our inlet mass flow rates times enthalpy at the inlet plus kinetic energy at the inlet plus potential energy at the inlet. And then we're going to subtract out all of the mass energy flowing out with the mass. So we have exit enthalpy, exit kinetic energy, and exit potential energy. Okay. Okay, so let's talk about some assumptions and simplifications. Okay, so we have several that are given to us in the problem statement. So we have that this is steady. So that means I can get rid of these time derivatives. I also have that this is adiabatic. So I can get rid of Q dot. Right? I forgot to do this, but I'm going to highlight it now. So we're told that we can assume constant specific heat. So I'm going to write that down. I am also going to assume that I can neglect kinetic energy. So that means I can get rid of my V squared terms. And then I'm also going to neglect potential energy changes. So I get rid of my Z terms. And then last we have one inlet and one outlet. So I can get rid of my summations. Okay. Okay, so we are going to simplify the equations. Based on those simplifications, so conservation of mass just becomes zero is equal to m dot in minus m dot exit, or m dot in is equal to m dot exit, which is just some flow rate m dot. And we're already given that value, so that's good. And then conservation of energy becomes zero is equal to minus W dot of the control volume plus M dot HI minus HE. If you remember, W dot of the control volume is equal to W dot out minus W dot in. Okay, we don't have anything coming out, right? Just going in. So this means that we have zero is equal to W dot A plus M dot HI minus HE. All right, so I'm just gonna solve this equation for W dot A because we want to find W dot A anyways. So this is M dot HE minus HI. Okay. All right. I'm also going to make a substitution. So note that since this is air, we can write our M dot HE minus HI in terms of temperature and specific heat, right? So HE minus HI is equal to CP TE minus TI. Remember that one? Okay, so I'm going to now say that W dot A is equal to M dot CP TE minus TI. Okay. Okay, so we have an equation that is quite useful for us to find W dot A, right? But we don't know a few things. We know M dot, we can figure out CP, and we know the inlet temperature, but we don't know the exit temperature yet. And we also don't know W dot A. Okay, so we're gonna leave this equation where it is right now because we can't go any further with it. And instead we're gonna have a look at our isentropic system because we were given isentropic efficiency. All right, so we can do that next. So next we'll look at the ideal system. All right, so we have our compressor. This is ideal. So we have our ideal or our isentropic power input. And we have our exit pressure is still 800 kPa because that has to stay the same. And then we have our exit entropy has to be the same as our inlet entropy. And then for our inlet, we're going to keep our inlet conditions the same. So we still have 100 kPa and a temperature of 12 degrees C or 285 Kelvin. All right, so we would like to know SI so that we can find SE, right? And then TES. Okay, so our ideal compressor conservation of energy equation is going to look the same, except for our exit is going to be the isentropic version of stuff, right? So we have W dot of our isentropic compressor is equal to M dot times HES minus HI, which is M dot CP TES minus TI. Okay. So since this is isentropic, so ideal equals isentropic, we're going to use our ideal gas isentropic relations. To find TES. Okay, so the relationships that I am referring to are the ones that we derived in that side-by-side derivation stuff. So if I go back more, so I'm talking about these ones. Okay, so we can relate ratios in temperature to either ratios in pressure or specific volume. In this problem, we're given pressure, so I'm going to use the equation on the right-hand side here, okay? Which is the following. So we're going to use TES over TI is equal to PE over PI raised to K minus 1 divided by K. All right, and just remember, K comes from the table. All right. Okay, so we need CP and K values for air. So we're going to use this table A2, which fortunately I have included this time. All right, and so we are going to use our temperature of so we know we need to pick a temperature, right? So we're going to use a constant CP. We know that our inlet temperature is 285 K. And we expect that the exit temperature is going to be higher. So we want to pick something that's convenient from the table that's not going to require us to interpolate. So what we're going to do is we're going to start with 350 as kind of an initial guess. All right, and so we have that our CP is 1.008 and then K is 1.398. So CP and K at 350 K are the following. So we have CP is 1.008 kilojoules per kilogram K, and then K is 1.398. All right, so I am going to put these values in for here, and K goes in here. All right, so we can solve this now for TES. So TES is TI times the pressure ratio all right, so I can plug these in. So I have TI is 285 Kelvin. And then our exit pressure is 800 kPa divided by our inlet pressure is 100 kPa. And then we have 1.398 minus 1 divided by 1.398, which gives us, 515.2 Kelvin. All right, and so now I can use this to find my ideal power input. So I will take this guy and put it in here. So W dot S is CP, sorry, M dot CP times TES minus TI. So we have, I think it was 0.2, is that right? 0.2 kilograms per second times CP, which is 1.008 kilojoules per kilogram Kelvin. And then times our difference in temperature. So we have 515.2 minus TI, which is 285 Kelvin. All right, so we find W dot S is 46.4 kilowatts. All right, so this is our ideal power input. Almost done. So we want to find our actual power input, but we are given the isentropic efficiency, right? So since we know eta C is 0.8, this is W dot S divided by W dot actual. So we have 46.4 kilowatts divided by W dot A. If we solve this equation, we get that W dot A is 58 kilowatts. Okay? Yeah.
Go over again, how you just came up with the temperature there for CP.
This equation, the top one?
Like, where does 350 Kelvin?
Yeah, so that's a good question. So, okay. We're using a constant specific heat, right? And so we have to pick a value from this table, right? And we technically, when we do a constant specific heat assumption, normally what we would do is take an average of the inlet and outlet temperature and pick a CP based on that average. We don't know the exit temperature yet, right? We know it's going to go up because it's a compressor. And we know the initial temperature is 285, but we don't know by how much it's going to go up. So what we did was we took a guess of 350 as being the average between the inlet and the outlet. If you wanted to solve this problem exactly, what you would want to do is iterate, essentially. So you'd have to numerically do this. So this is kind of a simplified way of solving this. So when we don't know the exit temperature and we're still going to assume a constant specific heat, we have to take a stab. And so we picked something that didn't involve interpolating, is where the 350 came from.
There's no methodology, I think it's gonna be this.
Yeah, so I would be, to be honest with you, like I would not give you a problem like this on the exam because it takes some guesswork and I don't like that. If you said, I'm gonna just take 300 to be my CP because that's the inlet temperature that I know, I'd be okay with that. If you wanted to do this very exactly, you would say, okay, I'm gonna take a guess as 350. I solved this whole thing and I found out the exit temperature is 515. So now I know an exit temperature. So I can calculate the difference, go back and check like how wrong was the CP I guessed, and go back and like keep doing that until you converge, is the true methodology. Does that make sense? Okay, that was a good question. Thank you for asking. So if you remember when we were doing this equation or this problem and we got to conservation of energy for our actual system, we said, well, we don't know the power input and we don't know the exit temperature, so we couldn't solve for either of those with this equation. Now that we have W dot A though, we can find the exit temperature. So I'm gonna call this equation star with the teal. So to find actual exit temperature, we'll go back to the starred equation. So we had that W dot A is equal to M dot CP TE minus TI, and now we have all of that information. So we have that TE is equal to TI plus W dot A over M dot CP. So we have 285 Kelvin plus 58 kilowatts divided by 0.2 kilograms per second times 1.008 kilojoules per kilogram Kelvin. All right, and so we get that TE is 572.7 Kelvin. Okay, and then last but not least, just very quickly, so nozzles are nozzle. So nozzles are the last kind of flow device that we've talked about in this class, so we should talk about efficiency for them as well. So these devices are steady, isentropic, or sorry, adiabatic. And when we compare an actual versus an ideal system, we're going to take the same approach as we have before. So all of the inlet conditions are going to be the same. So we're going to have PI, TI, HI, SI, and then the inlet velocity this time, as well as an MDOT. All right, because a nozzle is meant to accelerate the fluid, so we want to know about the velocity, of course. And then we'll keep that the same for our ideal system. So we have all the same inlet stuff: pressure, temperature, enthalpy, entropy, velocity, and mass flow rate. And then for the exit, our exit actual system will have our exit pressure, temperature, enthalpy, entropy, and velocity. And then for our ideal system, the exit pressure will be the same, but we will have everything else different. So we will have a different temperature because it's isentropic, a different enthalpy, a different entropy, where the entropy of this exit is the same as the inlet. And then we also have an isentropic exit velocity. Okay, so these are all of our isentropic exits. And then nozzles don't have any work input or output from them, okay? So if we want to find the efficiency of a nozzle, we do a ratio of the kinetic energies. So we have the actual kinetic energy at the exit divided by the isentropic kinetic energy at the exit. All right, with the idea being an ideal system is going to accelerate the fluid more than an actual system. Okay, so this one is actual exit kinetic energy, and this is our ideal exit kinetic energy.